Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together.
So optimization problems are, I think, one of the great values that calculus can provide to the real world. But we have to give you problems that obviously have solutions and that we can do with what you have gained knowledge-wise to now. So your goal is to read and understand the goal of the question. Drawing a rough sketch definitely helps. You're going to identify a primary equation, and that's going to include whatever object you're wanting the max and min of. And then if needed, you're going to get a secondary equation so that you can have fewer variables. And we're not going to put in, if numbers are varying, we're going to leave them as variables until the end. So I'm going to refer back to this quite a bit, so that's why I have this already written out for us. So we're going to first read and understand the goal here. You have a piece of cardboard that is 108 square inches, and you want to create an open box with a square base of maximum volume. What are the dimensions of the box? So my goal is to get the dimensions of the box. So my goal is length by width by height of a box. And it did say square base. So that means two of my dimensions are the same. And it did say it was open on top. Okay. So we're just going to take this 108 inches and we're going to be cutting up into pieces and kind of taping them together, it looks like. So we need that rough sketch, kind of got it going here. Identify the primary equation. What do you want to max or minimize? Well, we want to maximize or minimize the volume. So x by y, I'll call that, that way I have a square. So my primary equation is going to be that volume, because that's what I want to maximize, right? And that would be x squared y. I have too many variables. I have x and y. So I'm going to have to do some kind of secondary equation to eliminate some of those variables. That's what we're talking about. So how can I do that? Well, they said that my cardboard was 108 square inches, right? And my cardboard's going to have to be cut apart into 5 sides. Well, 5 sides, that would be my surface area, right? So it looks like I'd have the base, so that 108 inches would be shared between my base and my 4 sides, because that's open on the top. My base is a square, and the 4 sides would be x by y. Okay, I can solve for y here. No worries. And the 108 got to stay in there because it's consistent, right? So 108 minus x squared equals 4xy. So divide by 4x. Okay, 108 divided by 4 is 27. Minus x to the negative 1, right? Minus 1/4 x. That way we don't have to use quotient rules. Okay. No, I'll leave it as it was. We'll make it, keep it cleaner. If I had an eraser, it would be here somewhere. Oh well. I'll just leave it as 108 minus x squared over 4x. But now we need to substitute that in. Okay? They gave us no other numbers, so we're here. So we would have volume equals x squared multiplied by y, which would be 108 minus x squared over 4x, which would equal 108x squared minus x to the 4th. And I'll go ahead and write those as over 4x separately, because that's the same thing. So volume equals 27x minus 1/4 x cubed. Okay, so now I'm down to a volume equation because I'm wanting to maximize volume, and an equation based just off of x. So now I finally am going to derive. derivative of v, right? I'm going to use the v prime method so I don't have to write dy and dx every time. 27 minus 3/4 x squared. We want the volume to be maximized, so we're going to set the derivative equal to 0. So 27 equals 3/4 x squared. So 36 would equal x squared. So plus or minus 6 would be our critical numbers, but we know that we can't have a box length of -6, so that means our x must be 6. So our base is 6 by 6, and those would be inches. And then we need to get our height, and when we substitute 6 into here, 108 minus 36 divided by 36, we are going to get 3. So we have a 6-inch by 6-inch by 3-inch. We answered the question of what are the dimensions of the box. So I really recommend that you know your surface area equations for these, and that you know volume is area of the base times the height. Unless it comes to a point, then it's area of the base times the height divided by 3. And then sphere, you can also look those up. But those are some formulas that you're supposed to know from even back as far back as junior high. All right, so we did each of these steps for that problem. All right, read and understand the goal. 2 posts, one 12 feet high and the other 28 feet high, stand 30 feet apart. They are to be stayed by 2 wires attached to a single stake in the ground. The wires will attach to the top of the post. Where should the stake be placed? Okay, so we're going to draw a rough sketch. So we got a 12-foot high post, and it's going to stay 12 foot. It's not going to change. And one that's 28 feet tall. And they are 30 feet apart. Okay. They are to be stayed by 2 wires attached to a stake on the ground. So we're going to need a stake on the ground. And the wires will attach to the top of the post. Boom. Boom. Oh, I forgot to finish the question. Where should the stake be placed to minimize the wire used? Okay, so I'm going to call this wire A and this wire B. So we want to minimize the length A plus B. Okay. And our goal is to find out where the stake is. So does the stake go here, here? Do I move it closer to the 28 foot? Do I move it closer to the... What do I do? So I'm going to call this X, which then means this is 30 minus X, right? Now, we have 2 right triangles here because you wouldn't make the post not perpendicular to the ground. So we would have A squared equals 30 minus X squared plus 12 squared. And B squared would equal X squared plus 28 squared. So by substitution, our length is going to equal the square root of 30 minus X squared plus 12 squared plus the square root of X squared plus 28 squared. Okay, so the length of the wire is going to equal that. Let's go ahead and simplify this out some. because I'd rather not have the chain rule. Now remember, 30 minus x is going to be 900 minus 60x plus x squared, and then we're going to have plus that 144. So we can really write this as length equals, we'll go ahead and switch it to powers, x squared minus 60x plus 1044 to the 1/2 power plus x squared plus 784 to the 1/2 power. Okay. Now we can finally derive, switching colors for that derivative, right? 1/2 x squared minus 60x plus 1044 to the negative 1/2 times 2x minus 60 plus 1/2 x squared plus 784 to the negative 1/2 multiplied by 2x. Or the derivative is 2x minus 60 over 2 square roots of 2x over 2 . So we got that, right? Now, can these things all divide by 2? Yes. Also, aren't we getting ready now to put this in as 0? Absolutely, again, yes. Okay. I'm going to go ahead and move this to the other side as well as dividing by 2. So I'll have negative x over x squared plus 784 equaling x minus 30 over there we go. Now, can I square both sides of the equation? Absolutely. That way I don't have all these radicals to deal with. I'm squaring both sides of the equation. So we have x squared over x squared plus 784 equals x squared minus 60x plus 900 over x squared minus 60x plus 1044. Okay. Cross products, right? So x to the 4th minus 60x cubed plus 1044 x squared, that would be for this one, equals x to the 4th minus 60x cubed plus 900x squared plus 784x squared minus 47040x plus 705600. Whew. Well, that's fun. The x to the 4th cancels the x to the 4th. The 60x cubed cancels the 60x cubed. So if I were to bring this over to this side and combine like terms, we could quad formula. Let's see. That would be 144. So we would have negative 640 x squared minus 47040x sorry, that's positive 640. And then plus 705, 600. Okay, So we can go ahead and do that quadratic formula. Okay, 105 over 2. And if we did a minus, 21. Remember 105 divided by 2 is 52 and a half. So 21 or 52 and a half. Those are the answers we're getting. The thing is which one's going to work here? So X is labeled as the part right here. And we don't want to go 52 and a half feet over here because we'd have to use a lot of wire to get to it. We want this to be in between the 2 points. So 52 and a half is outside of our window. So we're going to want to be 21 feet away from the 28-foot post, which leaves us 9 foot away from the 12-foot tall post. So we want to split it up to where it's 9 and 21. That way we can use the least amount of wire as possible and still get the job done. Okay, another word problem, because these are all going to feel different. And that's the whole thing about why we're going to read and draw and look and read and draw and look, right? So an offshore oil well is 2 kilometers off the coast. So, all right, we have a coast. Brown for sandy beaches, right? And this oil well is out in the ocean, so water, right? 2 kilometers. The refinery is 4 kilometers down the coast. Okay, so I drew the coast, so 4 kilometers. Laying pipe in the ocean is more expensive than on land, so which path should the pipe follow to minimize cost? Ooh. So ocean cost equals 2 times the land cost. Okay. Let's make X equal dollars per kilometer on land. That way everything's in kilometers. So this would be, so ocean cost would equal 2x. Okay. So they want us to lay pipe. We might be laying it just across the ocean and not doing land at all, but we're probably going to come down a little ways and then go out. So the cost of this would be how much ever it costs times the length. We'll call this length A. And this would cost 2x times the length, and I'll call this length B. So the total cost equals, let's call this not x but c. So this will be 2c. The total cost will be a times c plus 2b times c. And the c idea, that's just a constant. It's never changing. So could I have made it up and said $20 for this and adjusted? Absolutely. We could have done that however we wanted to. So here's the deal when we go to do this. I could do A and B, but I think that's the more complicated way to do it. Okay, here's what I would prefer to do, because we know the pipe does this, and then it's going to come out like that, right? And I'm still going to call this A and B, but I don't want B to have a complicated answer. So I'm going to call this X and this 4 minus X. Okay? So the cost, the total, will equal, when we know this is 2. A times C, but A is going to equal that 4 minus X, right? 4 minus X plus 2C times B. But I don't want B there. Okay? So we know in this picture that X squared plus 2 squared equals B squared. So B is going to be that square root function. So, boom. X squared plus 4 to the 1/2 power. Oh, and I forgot to do my A times C. Now C is a constant, it's never changing, so I could go ahead and put in $10 if I wanted to, for all that matters. I'm going to leave it as a blank right now. Total equals 4C minus CX plus 2C x squared plus 4 to the 1/2. Now everything's based off of X, where X isn't the length of A, it's the length over here. Let's derive. For C, C is a constant, so 4 times any number is going to be just a number, so when I derive it, I'm going to get 0. C times x to the first will just be C. 1/2 times 2C is C. X squared plus 4 to the negative 1/2 multiplied by 2x. Okay. Okay, so now that we have our derivative, now we can set it equal to 0. So 0 equals negative C plus C multiplied by x squared plus 4 to the negative 1/2, and that's being multiplied by 2x. And I want to be able to keep my picture Okay, so keeping my picture in the window, I went ahead and grabbed a second sheet of paper. So now that we know our derivative, we can set it equal to 0. Clean that up a little bit, right? Okay, I'm keeping my picture in the window the whole time so I remember what my variables are about. I'm going to add the C over. Okay, and now we can see that the C's are going to cancel out, and I can multiply this side over. At this point, we're able to square both sides. Subtract an x squared, square root everything, and divide. So we'd get 2 divided by the square root of 3. Or 2 square roots of 3 over 3. So remember, this x is right there. That's the 2 square roots of 3 over 3. So how far do we go down the land? Well, our a value is going to be 4 minus that 2 square roots of 3 over 3. So that's how far we're going to have to go down on land before we turn. And if you want to know what that was, that's roughly 2.8 kilometers. So we're not doing like a 50-50 switch here. We're going almost 3 kilometers down the shore before we go ahead and turn out to our oil well so that we can save as much money as possible. So if you happen to be the company owner, that's going to be what you're going with. Okay. Next fun problem. A steel pipe is being carried down a 9-foot wide hallway. At the end of the hallway, there's a right angle turn into a narrower 6-foot wide hallway. What is the length of the longest pipe that can be carried horizontally? So the important thing here is we're talking about that horizontal. We're not talking about, oh, I could like angle it up and like squish it in or something to that effect. No, maybe it's a really heavy pipe and you have it on, furniture movers or something. I don't know. But it's got to stay horizontal for this problem. So those of you creative thinkers, well, I love it, you might hold off on that. So let's get a picture drawn here. Okay, and we have to carry a pipe in. It's going to have to make this corner, right? So what's the longest that can be? I'll call this A and this B. So the pipe is going to be of length A plus B. But of course I don't want A and B because I really don't know much about A and B. Okay, I do know that this is 9-foot wide and that this is 6-foot wide. But I don't know anything about this part of the triangle or this part of the triangle, so I'm kind of up a creek without a paddle here. And I've seen students look at this for a long, long time, because right now we have a 9-foot, B, and an unknown piece. And we have 6 and A. We have 2 right triangles, but if I call that X and Y now, I have 4 variables, and that's not very helpful. So while some people would sit here and push through and push through and push through, what if instead we looked at an angle? Okay. So let's look at parallel lines cut by a transversal. Okay. What did this angle right here between the 6 and the A have to be the same as this angle right here between the B and the upright? The answer to that is yes, because they are on both in the top right corner of their respective parts, so they're corresponding angles. Boom. Let's call that alpha. Now, on this B here, we have the opposite and hypotenuse. Opposite and hypotenuse is sine. So sine of alpha equals opposite over hypotenuse. I'm going to use a capital B. Okay, here, cosine of alpha equals adjacent over hypotenuse. So B would equal 9 divided by the sine of alpha, and A would equal 6 divided by the cosine of alpha. Now they're both based off alpha. Now we can substitute. Okay, so our maximum pipe length is going to equal our A part plus our B part. Now I can derive. Okay. You can either quotient rule or chain rule. I'm going to quotient rule. Low D high minus high D low plus low, D high minus high, D low, okay. So this would make 6 sine of alpha over cosine squared minus 9 cosine of alpha over sine squared. And of course, we're going to put 0 in for p. Okay, I'll move it to the other side. 9 cosine of alpha sine squared equals 6 sine of alpha cosine squared. So 9 cosine cubed equals 6 sine cubed. Or we could divide by cosine cubed to get 9 equals 6 tangent cubed. So 3/2 equals tangent cubed of alpha. Okay, now I'm finally to the point where I can get a calculator in here, right? I'm in radians, I'm okay with that. I generally work in radians, but we're gonna have to do the third root first. Okay, so we get that, right? We're going to do inverse tangent. And I'm in radians, so 0.85 radians. If you did it in degrees, it's fine, because the answer isn't about my angle. Alpha equals 0.8528 radians, because that's what I'm in. But I want to know what's a plus b. So 6 divided by the cosine of that. A is approximately 9.12. B is 9 divided by the sine. 11.95. So if I were to take this and add this, my total approximate length would be 21.07. Okay. So I can do approximately a 21-foot long pipe and be able to make this turn between a 9-foot hallway and a 6-foot hallway. So don't be afraid to switch up and use other methods. You don't have to just stick to the Pythagorean theorem or volume or whatever. Sometimes trig can come back in and help you. It may not have seemed like it at first in this problem, but that was going to be our shortest way unless you wanted a million variables. So remember, keep going through those processes. What is the best thing I can do? How can I bring this in? How can I compare? How can I get it down to one variable so that when I derive, I don't have to do implicit differentiation?
Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? And drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.